Good morning. So where would you like to, what things would you like to look at today?
Still stuck on the graph about the shrinking.
Shrinking and expanding?
Yeah.
Okay.
I think I'm more confused with like a 1.5, whatever, that.
Okay. So the question I was asked about is the, I can't remember the exact term either, but the dilation and it's that what thing causes graphs to be either stretched or shrunken? And we're going to take a look at an example like that. Let's just see. I just saw Deborah walk in, so I want to make sure. Yep. Okay. I suppose I will pick, let's see, that would be probably in chapter 1, huh? Oh well, close enough. I'm going to pick chapter 2, where I got a blank sheet here. All right, let's take a familiar guy like y equals x squared, and we'll pull a grid out here. And we'll show y equals x squared, and we'll show y equals 1/2 x squared. I'll pick a different color for that. So let's do red. What did I just do? Okay, now let's pick the pen. Now let's go red. So the question is, in this case, I guess you could say the one on the left is 1x squared, and the one on the right is 1/2 x squared. And maybe we could even do, let's do a third one. Let's do blue, and let's have that be y equals 2x squared. Now, I won't be able to fit this all on here real neatly, but here we go. So first of all, black. Our standard y equals x squared. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And then you got the negative counterparts. And so there's your y equals x squared. And maybe at the risk of connecting that in a sloppy way, I'll leave it. Okay, let's do the blues now. Y equals 2x squared. Changing over to blue. Now, 0 is going to stay at the same place. And when you take 1 squared, you still get 1, but now when you double it, it becomes 2. 2 squared is 4, and 4 doubled is 8. And the other one's going to be off the map. 3 squared is 9, and doubled is 18. It's going to be somewhere up about here. Okay, off the chart. And then there's the negatives. Why are those not showing up? That must not be. I picked a stupid blue. Sorry. So hopefully this will show up. Okay, so you get the general idea. Now, the red, okay, 0 squared is 0. That's all three of these are in the same place when it comes to 0. When you do 1, 1 squared is 1, but half of it is 1/2. 1 squared is 1. I'm sorry, 2 squared is 4, but half of it is 2. What did I just do? Yeah, that's right. 3 squared is 9, and half of that is 4.5. 3, 4.5. And the counterparts? And, okay, so a fraction in front of a causes it, one way to look at it is to be squished. A whole number causes it to be stretched. And even though I didn't connect them, I think you can see the effect there. Yeah. Okay. So there was a question of the stretching part of a function. Yep. Yeah, I think the reason you don't remember doing them is because we didn't. However, yeah, let me, so just to, so this gets on the recording, question said, I don't remember ever doing the logarithm laws, and we didn't do them, I don't think, so that needs to be a correction on your sheet. Is that on the bottom? Which part of the sheet was that on? Which? Oh, yeah. Do you see how I have the second part of the chart crossed out? The first column, exponential laws, that should stay there. But the second column, you can go ahead and cross that out. What, didn't I give you that?
That left the column as symmetry. We didn't have the bottom part crossed off.
Well, that's not, that's stuff I just wrote over the top of the sheet. Yeah, the only one I left uncrossed out here under trig is graph, sine, cosine, and tangent curves. There are other things, but we just didn't quite get to them. So, yeah, the question was, did I give you the latest sheet? Actually, I did. But all the edits you see up here are just me taking a pen and literally writing over the top of the sheet. So, sorry, there's a number of edits you're going to have to make. Yeah, so would everybody cross out the second column of that chart, please? Deb? I think those were already crossed out, weren't they? Okay, underneath ratio identities, starting with sum and difference identities, the remainder of that column we did not get to, so just X those out, please. Okay, so sum and difference identities from there to the bottom. I think that's it on page 1. On page 2, okay, what's crossed out in this column on the right here? Starting with know and utilize the 3 sum identities, down to know and utilize the 3 half-angle identities. 1, 2, 3, 4. There's 4 there that need to be crossed out, and then the last 1, 2, 3, 4. That leaves 2 in between that should be there. And then the second half of the chart. And what's the last page? Okay, on the last page, cross out the sine law. That's A over sine A equals B over sine B equals C over sine C. I might have deleted it. Okay. That's okay. Here I see. Actually, you guys have a later copy than I do. Because I think I deleted those. I just plain took them out because I couldn't put a line through them. Yeah. So I think that page you're up to date on. Okay. Sorry about that. we're a little, I should have put a, yeah, I should have updated this on my review projection here. What's next? You know, you keep it too quiet in here and I may have to come out, I may have to pull out a quiz. Not really. I'm not going to. I didn't, that was not a threat. That was just kind of a joke. Yep, Matt. The remainder theorem. That's a good question. Okay. Let's see. That would have been in, yeah, chapter 3. So let me pick a spot in chapter 3 here. Okay. The remainder theorem. We don't need red. Okay. The remainder theorem was actually twofold. One is it tells you when a factor divides evenly into a polynomial because it comes out to a remainder of 0. And if it doesn't divide unevenly, it tells you what the remainder is, which doesn't complete the division problem, but at least its main use is, hey, does this divide in evenly or not? And the remainder theorem, if it comes out to a 0, tells you that it does. And then you don't have to waste time doing a long division only to find out it doesn't. So it's kind of a peek into the future. So let me do a quick example. Boy, I don't know. These are hard to make up. Let me see if I can find one relatively quickly. Okay, I'm just picking a problem from this one page in the book here where I have this polynomial, 2x to the 4th minus 15x cubed plus 23x squared and plus 15x minus 25. Well, actually, what the book says is, find all the zeros of this function. No sweat, right? Actually, there might be quite a bit of sweat here. I mean, unless you know, do any of you see the factors? No, not immediately. Okay. Do you remember? So I'll tell you what I'm going to do is I'm going to bump into the remainder theorem as we do this problem, and hopefully that'll be enough to answer your question. Plus, at the same time, we're going to review how to do these. Okay. So, man, how do I find a factor here? Well, wasn't the first thing we usually did the rational roots theorem, where we did this PQ thing? Remember that? And we would break all the factors of P down, which would be plus or minus 1, plus or minus 5, plus or minus 25. Okay, and Q, plus or minus 1, plus or minus 2. Fortunately, there's not too many Q's. So now the question is, what about the P over Q combinations? Well, we got plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 5 over 1. I don't know why I have two commas there. Plus or minus 5 over 2, plus or minus 25 over 1, and plus or minus 25 over 2. Yeah. Okay. So those are our candidates. shall we also take a look at Descartes' rule of signs here? How many sign changes does the polynomial have? See, positive to negative. So here's 1, 2, 3. So that tells me that for positive, we have what, 3 or any even number less than that? It could be 3 or 1, right? Okay, now let's quick do what's f of negative x. Okay, and then we'll count the sign changes. Negative x, that would still be 2x to the 4th. This one, when you take a negative and cube it, you're going to have a negative, and a negative times a negative is a positive. This one's going to stay the same. Okay, does that make sense to everybody? Now, how many sign changes? Just 1. So negative is 1. Now, do you see why I put that in both places? I mean, we found there were 2 scenarios for positives, 3 or 1, but we only found 1 for negatives. Okay, well, it could be 3 or 1 for positives, but there's only 1 possibility for negatives, so it's got to be 1 in both scenarios. Now, can you tell me how many total solutions there are in this problem? Right. If you count imaginaries, there have to be a total of 4. Yes, Christina, question?
Yeah, if there would have been just say 3 negatives, but cancel along with the 3 positives, then it would be 3 and 1 as well. For negative.
Yeah, then we would have had to, that's a good question.
Wouldn't the same.
Then, I guess I'll just do a separate page here. Then you would have had to do this. You have 3 or 1, and you have 3 or 1 for this one. Well, it could have been like this, but couldn't it have also been like this? So in other words, you got to allow for all combinations. So even though there's only 2 possibilities for positive, 3 or 1, and the other one has 3 or 1, it could be that the 3's are matched up and the 1's are matched up, but it could be swapped like this too. So then you'd have to have 4 lines. So anyway, that was a good question. So back here, we've got them all covered. Now the total solutions, I think I heard somebody say 4. And that means in this line, there can't be any imaginaries because we already have 4. And in the bottom line, we could have a 2 there. So here's like our 2 scenarios. And that makes sense. The imaginary column always has to be even. Why? Because if you get any root that's imaginary, its conjugate, remember that? The conjugate pairs theorem says there's always another one. And so if you ever get a non-even number in that last column, you know something got messed up. Okay, cool. We're in good shape. Now comes the wonderful part. We got to find out what works. Okay. There's both signs available, so I'm going to start with, how about good old 1? Always start with the easiest ones. Does 1 work? Now, maybe to eliminate some confusion here, I am going to free up this. Don't need this anymore. Okay. So now, what happens when you plug in a 1? Well, we got x to, that's 1 times 2 minus 15 times 1 plus 23 times 1 plus 15 minus 25. And I think it works. It does. It comes out to 0. Rejoice. So now you know positive 1 is a solution, and you just found one factor, x minus 1. Okay. And by the way, what I was doing right up here, By this coming out to 0, Matt, that was using the remainder theorem. So we finally got to your answer. So now, how do we find out what's left? Usually what we do is do some, what? Synthetic? Man, I got that stupid thing hidden. There we go. We got enough showing now. Okay, so we got a 1 out in front here. And inside we have what? 2, negative 15, 23. By the way, were there any missing powers? Okay, let's see. Bring down, multiply, add, multiply, add, multiply, add, multiply. Yep, we got a remainder of 0. And here's our polynomial that's remaining, and it should start with what? 1 less than a fourth, so a cubic. So it should be 2x cubed minus 13x squared plus 10x plus 25. Okay. Well, we got to start. Yes?
Okay. This could be a silly question, but like, I'm kind of confused on where the second like row of positive, negative, and imaginary numbers is coming from. The 1, 1, and 2.
You mean in the Descartes rule of signs chart?
Yeah, I understand like how you got the 3 and the 1 and 0, but I'm confused about the 1, 1, 2.
Okay. We found out that there were 2 possibilities for positive solutions, 3 or 1. Correct? Okay, now just think. When we checked out negatives, we found out that's always going to be just 1. Okay, so remember, these could be 2 ways, but this could always be 1. So couldn't it be 3 and 1? And couldn't it also be 1 and 1? Remember, this could be 2 things. Aren't these the 2 possible combinations? Do you see why I have a second
Yeah,
row?
to give do like the subtracting 2 from 3, is that what you did?
Right, I got 3, but then 3 minus an even number. Yeah, remember, any even number down from that until you get to 0.
That's right.
Yeah. Oh, okay. And anyway, you saw how why did I fill out this? Because they didn't total 4. Okay. Anybody else question before we go further? So now we got to factor this guy. You know what? Let's not give up on 1. Let's try 1. Well, I don't know. I don't have any space. I'm just going to do it right here. 1 cubed times 2, negative 13, plus 10, plus 25, and that is not going to work. So we're done with 1. Okay. Let's get negative 1 in there, huh? Let's see. Remember, we could have 1 negative solution. So let's try negative 1. Negative 1 cubed, negative 1 times 2, minus 13, minus 10, plus 25. It works. See that? Cool. So we got it. Negative 1 works. Thanks to the, Matt? Remainder theorem. Okay, so I need space, so I'm getting rid of this. So now we know we have x minus 1. We also know we have x plus 1. And we're going to do some synthetic to find out what's left. Bring down, multiply, add, multiply, add. Yeah, we get a 0, and here's the remaining thing. 2x squared minus 15x plus 25. Okay. We have a quadratic, so we could use the quadratic. Now, another thing, we've used up our negative answer, so don't bother looking for any more negative answers, because there only was one. So, I don't know, should we just go to, let's just use the quadratic for the remaining part. Let's see what we get. X equals minus b plus or minus square root b squared minus 4 times a times c all over 2a. What happens to that minus, that's 8 times 25 is what, 200? So I get 25, and that's plus or minus 5. So we're down to 15 plus or minus 5 over 4. Did you see what I did there? This is, I believe, if I multiplied it right, 200. And 225 minus 200 is 25. And the square root of 25 is, of course, 5, plus or minus. So what are our two answers? 15 plus 5 would be 20 over 4, which is 5. And 15 minus 5 is 10, and 10 over 4 is 5 halves. Okay, so real quickly, what did I find are the answers? They're hidden here. 1, -1, 5, and 5 halves. So this is the scenario we wound up with. 3 positives, 1 negative, no imaginaries. And we did it. We found the zeros of this thing. And one of the most important tools in that bunch is the remainder theorem. Yep.
I'm still confused how to get P and Q. I don't know where you get the numbers from.
Okay, you always just take the last coefficient, whatever it is, call that P, and the very first coefficient and call that Q. And then what I did is found all the factors of 25. Well, plus or anything that divides evenly into 25 goes on this line, and on this line, anything that goes evenly into 2. And then you got to find all the possible combinations of P over Q. So I was now.
I got the rest of that. I just wasn't sure.
Okay, yeah. Anybody else question about this one that's up here? The good thing about doing a problem like that, it took us a while. We just reviewed about 12 things. It was pretty worthwhile, I'd say. Okay, where else shall we go? Christina. Right. Thank you. Yeah, that's an often misunderstood issue. The question is, how do you identify if a function is even or odd? I wish they hadn't named it that. Because your temptation is, oh, all I got to do is see if it's an odd degree or if it's an even degree. No, that's not true. Actually, what they're really checking for, Christina, is if it passes the y-axis symmetry test, then it's even. And if it passes the origin symmetry test, then it's odd. So just think back. Remember I gave you 3 symmetry tests? I think that was last class. Okay. How do you check for y-axis symmetry? You plug in a value for x and plug in the same number with the opposite sign. And if the answers come out exactly the same every time, then it's got y-axis symmetry and it's an even function. How do you check for odd functions? Run the origin symmetry test, which goes like this. Plug in a number. Now plug in that same number with the opposite sign. If the answer comes out with the same number but with opposite signs in those 2 problems, then you have origin symmetry and you have an odd function. Now, here's what's cool about this more complete, this correct way. It'll even fit things like tangent x that has no exponent in it at all, which, by the way, is odd. And here's how we can prove it. For example, take what's the tangent of 45 degrees? 1, right? You remember that? What's the tangent of negative 45 degrees? -1. So you notice how the answer came out to the same number with the opposite sign. Aha! Now, of course, you can't stop at 1. You got to do at least 2 or 3. But so the cool thing is, an odd function doesn't even have to have a power in it. And so you were very right by saying, be careful. It's not just now. Most of the time, even functions are the ones with even powers, and odd functions are the ones with odd powers. But that can be misleading. And so make sure you run the test. Yeah, I don't know where I asked you about that, but that we didn't do real well on that question. So I'm glad you brought it up. So I don't know. I think we did a slide yesterday on symmetry. Is that true? Yeah, where was that? So I should just add on here from yesterday. That's an even function. Those are even functions up there. And down here, it doesn't have a special identifier like these two do. It's simply x-axis symmetry. Yeah, there's nothing analogous that fits there. But that's kind of, it really is better that this is on this page now, so I'm glad you brought that up. Didn't think of that yesterday when you asked. In fact, I think it was you that asked me about that. Okay, symmetry. Lined up. I know, weird stuff. It's strange old man memory here. What else would you like to go through? I know it seems like after all of that, I'm supposed to ask an intelligent question about all of that material? Well, there should be a bunch in there. You shouldn't be bashful now. Completing the square. Wow, good question. Okay, that goes somewhere way in the beginning. So I'm running out of pages, so I'm going to clone this. Okay, and then we'll stick this back over here. Okay, completing the square. So, complete the square. Complete the square. First, check to see if there's a coefficient out here. If there is, you got to get rid of it. We don't, so we don't have to factor anything out. Take half of the b term, which is 3/2, and then square that. Let's see, how are we going to do? So yeah, you know what? I almost need an equal sign here, don't I? just let me, I gotta get this, I'm having a little trouble setting this up. So we're rewriting it, and we're saying okay, take half of that. Okay, I'm finally getting my picture here. Take half of that is 3/2. Squared is 9/4. Okay, so now you can write this as x plus 3/2 squared. And then once you're there, it's pretty easy because you can take both square roots. And then you can subtract 3/2 from both sides. Okay. Anybody have a question about that particular one? Because I'm next going to do one where we have a coefficient there. Okay, to do one with a coefficient there, there's actually two things we could do. I'll make a page, excuse me. Okay, so one with a coefficient might look like this. 2x squared minus 7x equals 3. Solved by completing the square. I can't right away do anything with this because of this confounded 2. I have two options. I could just get rid of it by divide. If you have an equation, you could just divide both sides by 2. So then you'd have x squared minus 7/2 x equals 3/2. Now take half of the b term, which would be 7/4 squared, would be 49/16. And now you could go ahead and complete the square. Let's see, that's 24/16 plus that, 73/16. Okay, technique 1. Everybody follow what I did there? I'm going to do it a second way in just a moment. Yeah. Where? Everywhere? Okay. Starting with the first step. I cannot complete the square when there is not a 1 sitting right here. Okay? So I had to figure out how can I get rid of that 2. Well, one legal way, since we have an equation, is divide both sides of the equation by 2. When you do that, you get x squared. Of course, you got to divide everything by 2. So I have x squared minus 7/2 x minus 3 equals 3/2. Now, the old technique says, now I can go ahead and proceed. Take half of this guy, 7/2 times 1/2 is 7/4. Yes? 7. Take half of it. You get 7/4, and then you take that answer and square it, and I get 49/16. Add that to both sides, which I did. Okay. Now this is a perfect square trinomial, so you should be able to write it as a binomial squared. Square root of this goes right here. Square root of this goes right here. The sign from the middle term. And then here I just did some arithmetic. I said, let's multiply top and bottom by 8 so that we'd have a common denominator. So this is 24/16 plus 49/16, which if I added right is 73/16. Then take, from here on in, you probably, okay. Now, should I get the second technique? Another way to do the same problem. So what was it? 2x squared minus 7x equals 3. Remind me of that. 2x squared minus 7x equals 3. Okay, so here's another way to do the problem. Instead of dividing everything by 2, I could factor a 2 out. I could go like this. 2 times the quantity and leave a space inside the parentheses for completing the square. Now, even though the 2 is still on that side, notice I now have my desired 1 there. So now go ahead and complete the square. What's half of this? 7/4. What's 7/4 squared? 49/16. Add that. But now, what did I just add to the left side? This is, be careful, what did I just add? I didn't add 49/16. Didn't I add 49/8? Because isn't that, what's 2 times 49/16? 49/8. So because I added 49/8 to the left side, got to add 49/8 to the right side. Okay, now, this is x minus 7/4 squared. This is, oh, let's get a common denominator here. 24/8, so 73/8. And then divide both sides by 1/2. Now from here on in, it's going to be identical to the previous page. So these are both ways. My first technique is probably, I don't know, it's probably more direct, but they're both legal. Yeah. That's called copying it wrong. Sorry. Thank you for spotting that. That's going too quick. Yeah. Yeah, was that a mystery? It should be, because it was, yeah. So anyway, I didn't finish it, but the rest of this would look exactly the same. John?
What happened to the 2 outside of the
What I did is divided both sides by 2. So this went away, and that's why this became, yeah. Divide both sides by 2. Good questions. So there's a, now maybe I should show you one more issue related to completing the square. And that is, a common problem that they kept giving you was, oh boy, these are going to, the trouble is they're such stinkers to make up. That's when you have this big old polynomial with x's and x squareds and y squareds and constants, and they say to you, oh, this is a circle. Find the equation of the circle, or find the center of the circle in the radius. And you're like, that's a circle? And what you're headed for, and this would be a good thing to review, remember this form? This is the general form of a circle. It's probably it should be on your sheet. If it's not, you want to add it. And where HK are the coordinates of the center of the circle, and R is the length of the radius. Well, to achieve that, you may have to take a bunch of x garbage and complete the square, so you can get it in this form, and a bunch of y garbage and complete the square, so you can get it in that form. And once you got it in this form, you can say, oh, I can tell you where the center is, I can tell you what the radius is, and so I got this baby nailed. You got it all then. So do you remember, it's just I can't come up with an example. It would take me 15 minutes to make one up, and I'm not going to, or 10 minutes, and we don't have it. So, but I wanted to make the point. This was a typical application of completing the square. And if you look up in the index of your book under completing the square, I'll bet you can find some problems like this. That would have been a good suggestion for me, but I still think it would have taken too long. Yeah. Well, we're getting close to the end. You can stick around, but I do want to say I appreciate you being in my class. This is really fun for me to do, and the fact that you're in here means I have someone to teach, and you guys are fun to teach. And I want, wherever you're headed with your math, I wish you well, and thanks for taking the time to fill out those evaluation forms, and God bless you no matter whatever you're headed for. Stop in and see me. If you have some math questions, I don't care what class you're in, or some non-math things, come on in. See ya.